Now we'd like to talk about kinetic theory. In chemistry, we like to focus on the molecules or particles in a system and how do they behave. So this is where the kinetic theory comes in. In particular, we usually focus on gases because gases change the most of the states, between solid, liquid, and gas. They all are affected by various factors, but gases in particular. So we're going to focus on that. The kinetic theory itself involves these three factors: pressure, volume, and temperature, as well as many more we focus on. And ultimately, let's say we let this be a molecule of gas. Of course, this is huge. This is 1 trillion times bigger than a real gas molecule that's in this room. But you can see that if I drop this, it goes in a straight line. And we can imagine if it goes about 1/6 of the speed of light, super fast, it would be bouncing off of everything. See how it's colliding off the bottom here? It can collide off the wall. So collisions that occur are actually pressure. That's how we measure pressure. We talk about collisions. That's part of the kinetic theory. So straight line here. And also, if it bounced off the wall or if it had corners and stuff, this would kind of go randomly. And we say that the kinetic theory the molecule would also go continuously. So we have continuous, random, straight line motion. Kind of like this super ball would have if we could let it go and shoot it super fast. When it comes to volume, volume means you have the volume of this actual particle. Of course, these particles are extremely small. They're 1/10,000,000th of a meter in diameter. And so we like to say that the volume of this gas molecule has really no comparison to the space that it takes up. In real life, it does. But for the theory, we say that volume really can be ignored for the size of the particle compared to its container. And then we've already talked about temperature in detail. It's the actual how fast do these molecules go, and it takes the average of. In real life, this theory doesn't work. There is some volume in this particle. They do have some attraction toward each other. This theory says that there's no attraction between the particles, but there are. For instance, we know that a solid, like the tables that are in our rooms and this board here, they're solid. The attraction between the molecules there is quite strong. If we turn it into a liquid, like what I have in here, I've got liquid in here, the attractions are still pretty strong, but they're not as strong as a solid because they can move. Like if I take this out, you can see this can move. And then a gas, the particles are pretty much random altogether. They're going all over the place, not strong attractions whatsoever. Another interesting thing now is if we focus on the three different states: gases, liquids, and solids. And again, gases are the most changeable. So let's look at that. A gas, its volume can change a lot. Like if you look at this can, you've all heard of silly string. This is an aerosol can, so they pressurize stuff in the can, and you can see what happens here. Okay, it comes flying out of there because there is a drastic volume change from being forced in this can to all of a sudden now it's open. And so the volume can expand greatly or contract greatly when we're talking about gas. When we're dealing with pressure, pressure is very simple. It's the force per unit area. So when I push on something, that is a force, that's pressure. But again, we like to think of pressure in terms of collisions, molecules hitting each other, colliding off the wall. And the way we measure pressure is we use something called a manometer. This is a manometer, a YouTube manometer, and I'm going to show you a couple different kinds. Right now, if you can see this, the water levels on each side are the same because this would be considered atmospheric pressure out here, the air pressure. But watch what happens. Even if I just push this in, it didn't move much, but you'll notice now we call this the gas pressure. It's contained, and outside is the atmospheric pressure. Notice that the gas pressure went down and the atmospheric side went up a little bit. So based on the whole definition of pressure, which is force, the gas pressure must be more than the atmospheric pressure because it pushed more. Okay, now I'm going to cheat a little bit. Now you can see that it's way down here versus up here, okay, in this manometer. The gas pressure is clearly more than the atmospheric pressure because it pushes more. Now we can actually take a difference here. We can actually measure the difference. And if we do that, we can actually calculate either the gas pressure or the atmospheric pressure as long as we have the pressure of one of those. Ambient pressure has a lot of values, but the one we use in chemistry is 1 atmosphere, which is sea level. That is also equal to 760 millimeters of mercury. And the guy who came up with this was named Torricelli. So that is also equal to 760 torr. And there's one more measurement that you'll find in your tires and on engines and a lot of other places. It is 101.3 kilopascals, and this is actually the metric unit here. All of these represent standard pressure. Why do we need it? So we compare things. Notice here that it's millimeters of mercury. So mercury is our substance that we use, and the reason it's got a very, very high density, a high specific heat, it's a very stable substance in terms of measuring pressure. Unfortunately, we can't use it in a school laboratory. It is against the law. So we have to then be able to convert not only one pressure into another using factor labeling, but also, since we can't use mercury here, we often will use alcohol in our thermometers. Doesn't work as good as mercury. Or we'll use water in our manometers. Like barometer is a form of a manometer. Okay, and I'm going to show you one in just a minute. When we calculate pressure, this has got water in it. So we have to actually calibrate that to millimeters of mercury.